Number 8. Sunlight whose visible wavelengths range from 380 nanometers to 750 nanometers is incident on a sodium surface. The work function for sodium is WO 2.28 eV. Find the maximum kinetic energy, Ke max, in joules of the photoelectrons emitted from the surface. Since we know 8A has the shortest wavelength, it means it'll have the maximum frequency or the maximum energy in this case. E photon can be converted to HF, and the F can be converted to V over wavelength. A wavelength can then be converted to 380 over 10 to the 9th meters. Then we have our Ke, which we're trying to find, and the W, which is 2.28 eV, which we can then convert to joules. We then subtract 5.23 times 10 to the negative 19 from 3.648 to isolate for Ke, and our maximum Ke is 1.58 times 10 to the negative 19 joules. 8b then asks for the range of wavelengths that would cause photoelectrons to be emitted. So first we need to find a threshold frequency. We can find a threshold frequency by the E photon equals Ke plus W, and since we want to find the minimum, we make Ke equals 0, and we plug in chug basically. H is equal to Planck's constant, and F could be converted to V over wavelength again, and our 2.2 eV is then converted to joules. We then want to isolate for wavelengths, which you get 3.0 times 10 to the 8th joules is equal to 5.5 times 10 to the 14th wavelength after we divide by Planck's constant on both sides. We then divide by the 5.5 times 10 to the 14th, which we then get 545 nanometers, and the range would be 380 to 545 because 380 is the maximum wavelength it can have, and 545 is the threshold frequency where electrons would start to be emitted.